This video is sponsored by CuriosityStream, home to thousands of documentaries and nonfiction titles for curious minds. So I figured it was finally time I do a little follow-up to a previous video I did, this one specifically, because I was getting the same question over and over in the comments. In that video we saw that in the game of asteroids, the shape of the, quote, universe you play in is topologically a torus. Because when you go off of one side, you come back on the direct opposite. And we can see the same thing here with the right and left. So the edges are identified with their opposite, which can be represented with arrows. And if you physically connect those edges, you end up getting a torus. It's topologically the same as the asteroids game, since topology doesn't care about bending and stretching. And from that, there were many comments asking, why isn't the asteroids universe topologically a sphere? And now I can see why so many people were asking that question. Because on a sphere, if you're living in that universe, surface, and you move straight up, for example, just go straight, you will come back to the bottom and just reappear where you started. Just like the asteroids game. And if you go to the left, your guy's left, you reappear from the right, back to where you started. So that matches the asteroids game. The problem is if you move in any other direction. You move, let's see, to the top right for you guys, up and to the right. If you just go straight, you will appear bottom left, back to where you started. And if you go to the top left, you'll reappear on the bottom right, back to where you started. So, on a sphere, no matter which direction you travel, you will come back to where you started. So with the rectangular representation, it should look like this. Any direction you travel brings you right back to where you started. But in the asteroids game, that isn't what happens. If you go up at an angle like this, then you'll reappear down here. Then you go off the side, and you travel off the edges a few times before you possibly come back to where you started. Like we just saw, this doesn't translate to a sphere. But it does translate to a torus. It results in kind of a winding path that loops around the torus as you, well, loop around the torus. See, representing a sphere topologically isn't as simple as directly connecting opposite edges like with the torus. You actually have to collapse all the edges to a single point, which would also technically cause warping that I wasn't showing in these animations, but hopefully you get the idea. So the paths along the asteroids game only seem to correspond to a sphere when you move straight up and down or left and right. But if you move in any other direction, then it only can correspond to a torus. So that's the explanation, but I figured I could use this time now to show some other ways in which a torus is not a sphere. Because there are some surprising things you can do on one, but not the other. For example, on a sphere, if you have two orthogonal circles, that is, circles whose tangent vectors are perpendicular at the intersection point, then the circles must intersect in two locations. One we can see here, and the other's hidden. But no matter how you draw those orthogonal circles, you get two intersections. However, this is not the case on a torus. You can draw two orthogonal circles that only intersect at one point. So there's something that can be accomplished on one surface, but not the other. But that's not the only example that has to do with loops on these surfaces. If a bunch of people on the surface of a sphere, like Earth, linked arms to form a loop, it is always possible for them to walk forward while never breaking the link, and eventually meet at one point, while getting very squished in the process. But mathematically, you can contract the loop to a single point. Even if everyone linked arms around the equator, they could maintain the link and eventually meet. The mathematical way to say this is that on a sphere, every loop is contractible. This is not the case with a torus. If people formed a loop like this, there's nothing that can be done for them to meet at a point without breaking the loop or digging into the surface. As they walk forward, they'd notice they aren't coming together like on a sphere, so this loop is not contractible. And this is a theoretical yet very unrealistic experiment you could do to determine whether you're living on the surface of a sphere or not. If you can find a loop that is not contractible, then you're living on something else. Then something I've talked about in detail in another video that's worth mentioning here is that if there were a torus planet, there could theoretically be wind blowing at all points on that surface at the same time. This is a continuous tangent vector field with no zero vectors. But if you close the hole to form a sphere, you'll see a zero vector is formed. In fact, since this is 3D, there has to be 2. This is always true. By something called the Hairy-Ball theorem, yes, that's a thing, on a sphere, a continuous tangent vector field must have at least 2 zero vectors, meaning on Earth at any moment there are at least 2 points where the wind is not blowing. Now this next example is more well known, and that's the 3 utilities problem, which has to do with a graph that can be drawn on one surface but not the other. The problem states that there are 3 homes and 3 utility companies which must connect wires to each of those homes without intersection. And for now you're confined to the flat plane. So this configuration is almost what we need. All utilities are connected to all homes. We don't need to connect the homes to each other, and same for utilities. But there is intersection, so this fails. And it turns out this is impossible to do not only on the plane but also on a sphere. You'll still get intersections. But on a torus, this amazingly becomes possible by making use of the hole. We'll directly connect 2 houses to the middle utility, and then the third connection is the one that will make use of the hole. And this will allow us to do all the other connections directly without any intersection. And we can also see this on the polygon representation of a torus. Just picture this as the asteroids game. We can make a few direct connections as shown, but then we can make use of the wraparound effect to make those last few connections that make this puzzle possible without any intersection. And what I also find interesting is the fact that a torus is homeomorphic to, and thus topologically the same as, a coffee mug. Thus the 3 utilities problem is possible on both of these surfaces. Notice that the hole of the donut that we had used to our advantage becomes the handle, or the space it surrounds. So now we make use of that to get the necessary connection that makes this puzzle possible using only the mug surface, which was shown in an older 3 blue 1 brown video. The reason why this works on a torus has to do with Euler's formula, and definitely not out of pure laziness. I'm going to link this James Grime video below that explains it, because honestly I would probably just say the same things he does. And it's not just the 3 utilities graph, by the way. The graph known as K5, which has 5 nodes that are all connected to one another, is impossible to draw on a plane or sphere without intersection. However, if we move to a torus, then it can be done. And while I'm sure there are many more examples, hopefully you at least learned the important life lesson that a donut is not a sphere. Unless it's this kind of donut. Then different story. But you get what I was saying. Anyways, before we go, I want to thank CuriosityStream, the sponsor of this video. This is a platform home to thousands of documentaries and nonfiction titles, many of which include topics within math, science, and engineering. One newer documentary you guys would likely enjoy is Precision, the Measure of All Things, which goes over the history of measurements, from the Egyptian equivalent of a ruler to modern atomic clocks. The history of measuring time, distance, mass, and energy are all discussed in this 3-part series, so it's a great blend of science, engineering, and also history. CuriosityStream is available on a variety of platforms worldwide, and it only comes out to $2.99 per month. But if you sign up by using the link below, you'll get your first month's membership completely free, so no risk in giving it a try. And with this, you'll have unlimited access to top documentaries that I'm sure many of you will enjoy. And with that, I'm going to end that video there. Thanks as always to my supporters on Patreon. Social media links to follow me are down below, and I'll see you guys in the next video.